Hello there.
Resistors are electrical components that resist the current flow from an EMF device. EMF stands for electromotive force. Resistors have unique color bands that signify the resistance. The symbol for resistance is R, with the unit being the ohm. As with capacitors, we present two equations. The first equation is based on the geometry of a wire and is based on the property of resistivity. Of particular note with this equation is that the resistivity and or the length of the wire increases, the resistance also increases. Decreasing the area also increases the wire's resistance. A table is provided in your notes for reference of common materials. The second equation is known as Ohm's law and relates electrical properties of voltage and current. In problem 1, we explore the idea of human resistance to electricity. So a human being can be electrocuted if a current as small as 50 milliamps passes near the heart. An electrician working with sweaty hands makes good contact with the two conductors he is holding. So here we have a resistance of 2000 ohms. The current is going to be 50 milliamps, which is to be converted to 10 to the negative 3 amps. What would the voltage be? What would the fatal voltage be if it's applied with 50 milliamps? Well, from Ohm's law, we know that V is the current times the resistance.
Goodbye.
We get 100 volts in this situation. Now, to put that in perspective, the outlets in your house right now, they're rated at 110 to 120. If you want to go find an interesting outlet, look look in your laundry room, washer and dryer. There's going to be a round looking outlet, and that's a 220 volts. So those kinds of machines require more voltage. Problem 2 becomes pretty difficult. We have here only a few things given to us, and you're going to have to apply any geometry skills that you have. Now, we're going to, of course, do this problem it's in such a way that we're not going to round until the end. So we have copper here, and copper, if you look at the table from above, has a resistivity of 1.7 times 10 to the negative 8 ohms meter. We're given a voltage of 110 volts. We're given a length of the copper wire is 1.5 meters. And we're given the radius of this copper wire, which means we're going to have to calculate the area. The
Could you
area
say that
for a circle
again, please?
is pi r squared. So in this case, we're looking at pi times 0.5 times 10 to the negative 2 meters squared. Of course, because it's centimeters, we have to convert that 10 to the negative 2. So here's our little predicament. We have the information. We're looking for current, I. And we understand that current is going to be based on Ohm's law, V over R. However, we do not have R. We can find R by using the first equation given, where that's density times the length. Sorry, that's not density. That's resistivity. Sorry, resistivity times the length over the area. Now, mind you that if I replace that R, right, then I can say I is equal to V over R. So I ends up being this whole thing right here.
Most impressive.
Now, if we do some keep flip change, I'll leave that as an exercise for you to confirm. I'm going to get V times the area over the resistivity times the length. So if I were to plug these numbers in,
I think I need a hug.
I get current 110 volts times the area, which we said is this thing, right? We're not going to round until the end. Don't forget the square. And then now for those of you keeping track of your units, you'll notice that over here I have a meter square, which cancels out with these 2 meters on here. We get volt over ohm, which is the appropriate unit for current, which will be an amp. If we were to plug this in a calculator, I'm going to round to the nearest hundredth. It'll be 3.39 times 10 to the 5 amps for our final answer. And notice we didn't round until the end. You have to be comfortable with your equations. You have to be comfortable with your Algebra 1 skills. It's a bonus if you're comfortable with your units. For your summary, explain the difference between resistance and resistivity. A good place to begin will be the symbols as well as the units, as well as what they really mean, what they actually do. For power, we have three different equations. These are all based off of Ohm's law, so they're derived from Ohm's law, but we have power involved as well. Power, of course, is the unit of watts. Power, in the traditional sense, is the amount of energy expended per a certain amount of time, which we call rate. Problem 3. We have a 120 volt potential difference. This, of course, is going to be our voltage. And we have a power dissipation of 500 watts. What is the resistance? Well, if we go ahead and use one of these equations, we have power is equal to V squared over R. And if we do some algebra and we solve for R, we're going to get R is V squared over P in this situation. Plugging these values in, we get a number of a resistance of about 28.8 ohms. For part B, at what rate do electrons flow? Rate electrons flow. Rate electrons flow. Folks, that's fancy talk for the word current. We're looking for I. Now, I know we got this value here, but if you want to wise up with these problems, do not use numbers that have been rounded. Let's see if we can find something in terms of the original numbers given to us that were not rounded, right? They gave us V, they gave us P, we want I. So we do have this equation that power is V times I. I want to get the I by itself, so that's going to give us P over V. And if we go ahead and divide these two numbers, the calculator will give you a repeating decimal. If we just round this up to the nearest hundredth, we get 4.17 amps for part B. Remember, the rate at which electrons flow is also known as current. Okay. Last time we introduced you to capacitors and the symbol for that, and as well as the symbol for the battery. We're going to draw a simple circuit here with an EMF and a resistor. So here's our EMF. EMF stands for electromotive force. An electromotive force is responsible for moving charge through a circuit. In this case, the charges are leaving from the positive terminal, traveling on this way, and then they're meeting resistance as they go through this resistor. The symbol for resistor, this is actually called a fixed resistor. And then, of course, our EMF device, which you've seen before, a battery, or a potential difference. Summary, what quantities affect current? What quantities affect electric power? So, for example, there's current, there's charge, there's time, there's resistance, there's voltage.
Could you say that again, please?